Welcome back to the start of Chapter 6. Today we're going to be going over 6.1 exponential functions. This is a new type of function, so I would encourage you to watch through the whole video and learn a little bit about this new function. This is what I think is interesting, one of the first mathematical functions introduced into the world. So in Genesis 1:28, God blessed them, and he said to them, "Be fruitful and increase in number. Fill the earth and subdue it. Rule over the fish in the sea and the birds in the sky and over every living thing that moves on the ground." So whether or not the function was calculated, exponential functions started with the first two people. And we're going to look at a little bit later a population of wolves and how they increase exponentially. And anytime population or virus spread or any sort of increase happens where the base, it determines how fast that thing is increasing. So if you have a friend and you tell your friend something, and then he tells two friends, and then they tell two friends, and then they tell two friends, eventually the world gets told, and pretty quickly. So that's what we're going to look at today, and I just think it's interesting that even though it wasn't explicitly mentioned, in the very first chapter of the Bible, we get an exponential function getting started. And so what do these exponential functions look like? They look like this. The exponential function has a horizontal asymptote at y equals 0. It has a domain of all real numbers. And it has a range starting at 0, but not including 0, going to infinity. And the function for the exponential function looks like this, where you have a being an initial value, b being the base, which is a positive real number that's not 1, and x being the exponential variable, where the variable is no longer on the bottom, but the variable is actually in the exponent now, which is new for this function. We've not seen a function yet where the variable occurs inside of the exponent. And so we'll look at a few functions and just determine, do these have variables in the exponent or not? And so here you see the variables on the base, and so this is a no. This is actually a polynomial if you remember back from chapter 5. Here we see an x up in the exponent, and so we could say, yes, this is an exponential. The next one looks linear. That looks like y equals mx plus b, and so we'll say no. And the last one, we see an x in the exponent, so we'll say yes, this is an exponential function. Even though it has that negative, that's okay. Exponents can be negative in the exponent. It's still an exponential function. So now we're going to look at what this looks like, and for a lot of these, it's really hard to do without a calculator, and so you'll see me using a calculator. That's just to get some values. We'll talk more about problems that do and don't need calculators with exponential functions. So for this one, we're just plug and chugging 3, because that's what evaluating f of 3 means. And so f of 3 equals 8 times 1.2 raised to the 3 minus 5, which is just 8 times 1.2 raised to the negative 2, which is 5.5556 if you round to 4 decimal places. And again, I got that last step using a calculator, although the first 3 steps we didn't need a calculator for. So we'll look at a few today where the very last step of the problem, you would have to have a calculator to evaluate. Otherwise, you would just stop right there. Okay, so we've got the first instance of exponential functions, which is exponential growth. And this is a function where a and b are both positive numbers. So the initial value is positive, a, and b is a positive base. And the rate of growth is proportional to the amount present. So here's an example. The population of China was about 1.3 billion in 2013, with an annual growth rate of 6%. This is all modeled in this exponential function right here, and they want to know, after a little bit of time, so in the year 2031, what will the new population be? and t is the number of years since 2013. So the first thing we're going to do is just figure out, okay, well, how many years have passed? And so we'll subtract those two numbers, and we'll get 18 years have passed. And then we'll just plug and chug 18 into our function. And so what that looks like is p of 18 years that have passed equals 1.39 times 1.006 raised to the t, where t is the number of years that have passed, 18. And like I said, this next step's a calculator, because without a calculator, that is not a problem that we're going to be able to do. And so we end up at 1.54 billion people. And so the population grew in 18 years from 1.39 billion to 1.54 billion. And that's kind of what I was saying, is that populations grow fast because they're working with a base and a variable that's in the exponent. So as x increases, so does the exponent. And that's an interesting result that leads to fast growth or fast decay, which is what was instituted in Genesis 1. Hence, all of the people in the world. All right, so what do we do if they give us a problem? And here's another wolf population one. It's a population again, and we've got 2 years, and we want to figure out what an equation that represents this situation would be. That we had 129 wolves in 2011 and 236 in 2013. So I'm going to write those 2 points first, but then I'm going to manipulate the 2 points to make my equation a lot easier to solve. So in 2013, it's 236. But what I'm going to do is I'm going to take a book out of the try it 3, the problem we just did, and say, let's call t time years since 2011. And that way we can rewrite this point as 0, 129, and how many years have passed? 2, 236. Because you can't go backwards in time, so we're just going to use that starting point that they gave us as our starting point for the problem, or for the time that's going to pass. And so I'm going to use the formula for the problem, which is f for the, exponential functions, which is f of x equals a b raised to the x. This is the general formula for exponential growth. If you scroll up a little bit, it says it right there. Exponential growth is ab to the x, where a is positive and b is positive. And the first thing I'm going to do is plug in the easier of those two. So I'm going to plug in 0 and 129. And so 129 equals a b to the 0. And anything to the 0 is just 1. So 129 equals a times 1. And so a is 129, and we have half of our equation already solved. The only thing that's left to solve for is b. And so then I'll use this red one. I'll say, okay, now that I know a, I'm going to plug all these numbers in and find b. And so using the red point, I'm going to say 236 is my output, or my y value, or my function, my f of x, is equal to 129 times b, because I don't know b yet, raised to the second, because that's 2 years have passed. I'm plugging in my input for 2. And then I'll solve for b. And if you solve for b, you get b equals the square root of 236 over 129. And because this is exponential growth, we can assume that that's a positive square root, because it said a and b are both positive numbers. And so we have our equation because we solved for a and b. This was the general form of the equation, and so our equation to model growth is 129 times root 236 over 129 raised to the x. Oh, I used the variable x, so I might go back here and say I meant to use t, but we'll just call it x. X is the number of years that have passed since 2011, and that equation could solve for that. All right, try it 5 is a little bit more difficult, but not much. I'm going to leave that to you to try, but if you need help or you want some assistance in where to go next, you can look at the completed notes online to get some help, or you could reach out to your instructor and ask for help as well. We'd be more than happy to help you. Here's an equation on a graph, And because it looks like the exponential function with the horizontal asymptote at 0 and a y-intercept and another nice neat point right here at 1, 2, it's actually going to be a really similar solve to the last one as well. So I'll leave that for you to try as well, because the steps aren't going to be any different, where you're just going to try to solve an equation f of x equals ab to the x using those 2 points. Using this red point and this green point, you're going to try to solve for a and b. And if you need help with that, look back up at try it 4, because we just did the exact same thing with slightly different numbers. All right, so now we're going to look at some applications of this, which come in the form of interest. One of the most common applications, other than population growth, is banks. Banks use exponential functions to accrue interest on loans and on investments. And so we've got a formula for compounding interest. And what this means in the very, very shortest version is, if I lend you $10 and I say you owe me $10 in a year, but I want interest. So actually you don't owe me $10, you owe me $11. And if I wait until tomorrow, technically I haven't lended you $10. Technically I've lended you $10.02. And it's like, well, hold up, I didn't lend you $10. I lent you $10.02. So I want interest on my interest. And then as it grows and grows and grows, I don't just collect 10% from you. I collect much more than that, most likely. And so we use this formula where we have an amount, a principal, or a starting, you have a total amount, a starting amount, or a principal. You have a rate, like a 10% interest rate. You have a number of times it's going to compound in a year. So I could compound it once a year. I could compound it 12 times a year. I could compound it every single day of a year. That's just the number of times we compounded in a year. And then a total time, that's how many years have passed. And what we're going to do is we're just going to use these equations to plug and chug some numbers and get some results. So for example, let's say I invest $100,000. There's my P, or my principal, at 12% interest. There's my rate, R equals 0.12. Remember, if you have a percent, you need to move the decimal over twice. P equals 100,000. Your rate is 0.12 or 12%. They're the same thing. It's compounded weekly. That means every single week. So that means the N is 52. And I want to know what it's going to be worth in 30 years. That's my time. And so I take those 4 things and I plug them into an equation. And I say the total amount after 30 years is going to be 100,000 times 1 plus 0.12 over, the N was 52, raised to the 52 times 30. Which is a really long and ugly equation if you don't have a calculator. And like I said, a lot of these, once we get our final result, we're going to be putting it in a calculator. And so after putting this in a calculator, we get 3,644,675.88. And so what that says is, after 30 years, I lent you $100,000, but you owe me over $3 million because I lent you $100,000 30 years ago, because the interest was compounding every week. And so that's a practical use of exponential functions. Another thing that we need to talk about while doing exponential functions is the number e. The number e is a pretty common number. If you look on your iPhone calculator or any calculator, you'll see a little like e. You'll see a little button that usually looks like e caret, or it's like e to the, or maybe it'll even say e and it'll have a little dotted box up here. It's just a common function that we get used to invest. And when you see e, kind of like pi, just think of it as it's just a number. It's not a variable that we're going to plug and chug numbers into. It is quite literally 2.718282. It's Euler's number, if you're looking to look it up and learn a little bit more about it. Swiss mathematician who realized a trend in compounding interest. And so we're going to use a calculator to just make sure we can plug and chug e to the negative 0.5 well into the calculator. And if you do that, you should get something like 0.60653. Again, no way to do that without a calculator. So this is just practicing looking at these buttons and these numbers on a calculator. And here's why that E matters. Because somebody along the way, as they were collecting interest on things, they said, you know, I don't want to just collect interest and compound it every year, like once a year. And I don't want to do it compounding like every month. And I don't want to do it every day. I want it continuously compounding all of the time. I want the number of times I compound to be the biggest number humanly imagined. I want to compound infinitely. Every single millisecond, I want it compounding on my interest so I can get the most return. And so instead of the formula where we had 1 plus inside of parentheses, he replaced that entire parentheses set with E. And he said, okay, now if you invest $100,000 for 30 years, and your initial investment is A, or your principal, $100,000, and you invest it at a rate of 0.12 again, and you invest it for 30 years, now your investment is worth, I'll type this in a calculator again, $3,659,823.44. And so what you see when you compare those two numbers is the difference between compounding numerically or compounding in intervals like months or years and compounding every second of every day literally infinitely. And so right here he made 3,659, and if we go back to the compounding monthly, he made 3,644. So he made an extra like $15,000 just by compounding, not changing the amount of money or the rate or the years that were invested. Just the way he did the math changed the amount of money made. All right, and lastly, we're going to look at one where it decays. Try at 12 says that radon decays at a continuous rate of 17.3% per day. So an important thing here to note is that the word decays means that our rate is actually going to be negative. So we're going to move the decimal over twice and get negative 0.173%. We start with 100 milligrams. And so what is the amount after 3 days, that's the A of 3, that's going to be left? And so we're just going to plug that into our formula where we say that's going to be 100 to start with, E to the RT. So negative 0.173 times 3 days. And if we type that into a calculator, 100 times E to the negative 1.73 times 3 for days, we get 59.5115 milligrams. And so what we know is after 3 days, it's decreased to 50. Well, it didn't even decrease halfway. It started at 100 and it's down to 59. So it lost about 40 milligrams in about 3 days, which isn't that much. But watch what happens after 1 year. So that means we're going to plug in 365 days for a whole year. We're still starting with 100 milligrams, E to the same rate, negative 0.173 times 365. So all we're doing is replacing that 3 with 365 in the calculator. And that rate's going to give us 3.77116 times 10 to the negative 26 milligrams. And what that means from scientific notation was that you'd have to move this decimal to the left 26 times before you got your amount. And so after a year, there is essentially none left. Sure, there's still a little bit left because matter's not going to be able to be destroyed, and we're never going to go down to zero by decreasing because there's an asymptote at y equals 0 for the exponential function. But it gets really, really, really small after a year. All right, so that's an introduction to exponential functions, a little talk about exponential growth, exponential decay, practical examples of what it looks like in the world, and the definition of how the graph looks and what the function looks like. Thanks for watching, and I'll see you next time.